Today's lesson is the last part of energy in this unit. Again, not in the course. Okay. So far we have covered two kinds of energy only. What two kinds of energy did we only cover so far? Kinetic and gravitational. The ones that make up what we call mechanical energy. Okay. So today we'll cover the third one. We still have two more. We still have two more to cover in the next upcoming units. But as far as this unit is concerned, this is gonna be the last one. Okay. So in this unit, or in your upcoming unit test, only three energies will be considered: EG, EK, and this one. Okay. So yes. So the definition of elastic energy is any energy that applies to something that is deformed. Okay. So deformed. What does deformation mean? A deformation, it like just and even in English means an object that changes shape without changing its mass. Okay, so all it changes basically its dimensions, its size, how it looks like. But if you keep putting it on a scale, it exactly weighs or has the same mass or is heavy all the time. Okay, it does not change how many particles are in it. It just changes how the particles are spaced out or compressed and so on. Okay, so this deformation could mean stretching, the opposite of stretching, compressing, and the only one that does not literally line up with these two, which is basically what? Twisting. Okay? And the only two we're going to do in this course are stretching and compressing. Only in specific physics and engineering courses, you actually do what we call twisting stress. Twisting stress, not in this course. Okay? So the physical symbol for elastic energy is, Junaid, you said it, E. By the way, just so you know, because here's the thing, we're also going to do electric energy, like the example I showed you yesterday. So when we do electric energy, technically we still could use what? E, but actually no. Most of the books, they actually use E, elec. Okay? So for elastic energy, we use just E. Now, do you make this uppercase or lowercase? Doesn't matter. As long as the actual capital E is there, the subscript could be uppercase or lowercase. I have a tendency to just make it lowercase. Okay? And again, as you can tell, all energies are always what? Vectors or scalars? All energies are always scalars. Okay? Right? Okay. Now, before we talk about the energy, before we actually talk about the energy, we have to talk about what force actually what makes elastic energy happen. Okay? All right. So whenever a spring is stretched or compressed, it is being driven away from what we call its natural state. Okay. By the way, even when you technically hang a spring, not when you go it on here, when you hang a spring from the ceiling, it is still slightly what stretched because of the force of what? Because of the force of gravity. Okay. However, depending on how the material of the spring itself, it could stretch a lot or a little. A lot would call what do you call a spring that stretches a lot, like so easy stretch? What's another name for those springs? Starts with S as well. Slinkies, exactly, yes. The opposite ones would be what? Would be the ones above your tire in your car, like the car shock absorber. Those are heavy, very thick, very industrially what? Stiff. Okay? So therefore, if acted on by an external force, whether you're pulling on it to extend its length or pushing on it to compress its length, the spring has to what? Technically, Newton's third law. Every action has a what? Has a no, every action has a reaction. Okay, so it always acts back by doing what? By exerting a force on you to what? To try to go back to its what? To its natural length. Okay. The opposing force actually is actually called what? Restoring. Because we. Oh yeah, come on. Announcement or what?
Yeah. Hello everyone. So on May 24th, there's the talent show.
Yes.
So right after the long weekend, basically.
Yeah.
Yes.
So the auditions ends on May 17th, and
So next week.
Yeah.
Your email will be posted around the school.
yeah,
So
you can send like your audition to.
Wait, you want your like auditions? You have to take video of yourself?
Yes.
I don't know after that.
Oh, it's a video, so like you're not going in and like actually.
oh, so it's not like American Idol where there's a stage and judges.
I'm just helping.
There is on May
Oh.
14th. It's a buyout. First, you send.
Yeah, no, we know it's like, but to audition. How does
Yeah.
that work?
It's through email.
Like
So
you send
you
a
just, like,
video
send
of
a
yourself.
video?
Yeah.
Yeah.
Who do you send it to?
The email.
The
Well,
email?
it'll be
Yeah.
posted
Yeah.
on the school.
Good.
It'll be posted on our school.
And the last day to send those auditions are 17th.
17th.
So next Tuesday. Yeah, by the end of next Tuesday. All right. And the actual show itself is one day.
Yes.
And it's
a
on the
buyout during third period.
Third period.
Yeah.
Okay.
See, that's the
Oh, no bio.
Thank
All right.
you.
Okay. So the opposing force that the spring is always putting in is always called the what? What does restore mean? When you restore something, you also restore it to what state? Final or original? You always restore things to what? To original initial state. Okay? All right. What are the two names? Listen up. What are the two names for the spring force? I always see two names. Either force spring or force restore. Those are the most common ones I've seen in physics textbooks. Yes?
Is the normal force technically elastic energy? Because when you're pushing something, it's technically.
Oh, sure. Absolutely. Yes. Yeah. Again, by the way, there is no surface that cannot be compressed. I mean, think about it. Even this brick. Obviously, bricks do not look what compressed, but are they compressed? Of course they are, because they're under huge stress or huge force. But the thing about the difference between a brick and a spring is that a spring stretch or a compress is very visible, right? Because it actually does change length or dimensions in front of your eyes. As for a brick, is it visible? But do you still know it's there? Of course it has, because it has to respond by compressing a little bit, which means it is technically pushing back. You're absolutely right. Yes. Normal force is one of the forms of restoring force. You're right. And again, by the way, Josh, I mean, you could even extend it to Newton's third law. Everything is what? Is a manifestation of Newton's third law, right? Every action has a reaction. So normal force and restoring force are Newton's third law, the specific examples. Yes. Okay? All right. So, now, the first one, I know that your slide might slightly look different than this. I changed the student version, but not the PowerPoint that I'm showing. But I'm just going to go through it. So, what you have in your notes, it says, when you deform a spring by stretching or compressing it, the formula that shows how much force the spring exerts or applies or puts in to fight back to restore its natural length is the following. And by the way, this equation, as simple as it is one of the basic equations of engineering, and even if you think about it, actually plastic surgery. Why? Because plastic surgery usually has to do with what? With the skin, which basically what is a deformed solid in a way. Okay? And this is the equation. The restoring force of a spring is equal to two things. Super easy. Linear equation. No squares, no halves, no weird math. Just something called the spring constant times how much did the length change how much did the spring change in its length? Okay, by either stretching it or compressing it. Okay. By the way, interestingly enough, about this equation, this only says what? Length what? Change. Which means it doesn't matter if you stretch the spring or compress it. Exactly. Whether you stretch or compress, if you stretch it or compress it by the same length, like if you stretch it by 10 centimeters or you compress it by 10 centimeters, the spring is gonna act back with the exact same force. It's just gonna be having a different direction. If you stretch a spring, the spring is fighting to get shorter. If you compress on a spring, the spring is fighting to get longer back to its original length. Okay? So the equation in mathematical form is this. This very easy equation is actually called Hooke's law. Exactly. Hooke's law, after Thomas Hooke, an English physicist who studied basically what we call stress and strain curves. If you ever become an engineer, especially a civil or a mechanical engineer, and you study materials, as Josh said, under stress like a brick, you will study a lot of what we call stress strain. You apply a stress, you get a strain. Strain means how long it gets, how longer it gets, or shorter, depends if you stretch or compress. And the stress is just another word for how much force you're putting on it. Okay, so this equation is K delta X. Although I'm going to get your attention to one slight hint here, or tip. Most books have a minus next to it. Why do you think they have a minus? By the way, we know that forces could not be negative. Yet many books, even your Nelson book, and maybe the university one we're using, has a minus next to it. Why do you think that they have? Just raise your hand if you think. Why would you put a minus to multiply the k delta x. Any idea? Josh?
Because
Uh-huh.
the length change is also going to be negative if you're compressing it.
Okay.
So it makes it positive.
That's one explanation. He's saying basically that depending on how you change the length, a minus has to be incorporated to account for are you pushing or pulling. But there's another reason. I'll give you a hint. Forces by nature are what? Vectors, which means what? Whenever you actually what? Push on an object, what does the object do? Push back, which means does it go in the same direction or in the opposite direction? Exactly. So they are treating a force as a what? As a vector when they put the what? When they put the minus. However, if you don't put the minus, you treat it just as a what? Which means do you care about the direction or just the what? Magnitude. Thank you very much. Awesome. I only care about magnitude. That's why I always what? Just provide the equation this way. And even when I think of it, I think of it this way. Because I'm always going to give a diagram where I'm what? Acting opposite. Sorry, the spring is acting opposite to how you're acting on it. Just so. So now you know, if you ever see a minus, it's not really a big deal. They're just putting a vector spin on it.
So what do you mean?
Nothing. You still think of it the same way. The only reason they're putting a minus is to emphasize the fact that the spring is always pushing opposite to how it's being pushed on. You see what I mean? They're always just putting it a minus. That's it. Yep. Exactly. Same idea. It's just going to give you a negative value, which is not really negative force. It's just acting in the negative direction to whatever the spring is doing. That's it. This constant K actually has a very well-known and actually a very descriptive name. It's actually called the stiffness of what? Of the spring. Okay, when you describe yourself as stiff, like when you get up in the morning and you feel stiff, what does that mean? Are you loose or opposite of loose? Exactly, you're what? You're very like clumped up, right? So a stiff spring, which one is a stiff spring? A slinky or the car shock absorber? Which one is more stiff? Exactly. Stiffness just means what? How hard is it to what? To deform, either stretching or what? Compressing a spring. Stiffness is just telling you how hard it is to apply force. To apply what? So to apply force to get what? Change in length. Yes. By the way, some people call it the spring constant. That's why I'm using two names. Some books call it the spring constant, and some books call it the stiffness constant. I like to call it the stiffness constant. Okay? It tells how difficult it is to deform the spring from its natural state, from its natural non-extended or non-compressed length, which is the length you get when you just put it lying horizontally on a table, not being stretched this way or compressed this way. Okay? All right. Yes. Okay. Let's go to the next slide. Okay. If you rearrange the formula for Hooke's law on the previous slide, we have what? The only way to rearrange it, ditching the minus, if there was ever a minus in the way they give it to you, is K equals what? The force of the spring, or the force restored, because remember we have two names, both of them mean the same thing. The force the spring applies on you, divided by delta x. Okay, let's play with the units. What's the unit for absolutely any force? Any force is newtons. And what's the absolute unit the unit for absolutely any kind of length? In standard units, it would be meters. Yes, which means by replacing physical quantities with their own units, we see that the standard unit for the stiffness constant lowercase k, by the way, it's always lowercase k. I don't care what physics you ever do, it's always got to be lowercase k. Is basically this. Yeah, that's the stiffness constant unit of any spring. By the way, again, of a spring, or when plastic surgeons, choose actually, like for example, what's a very common procedure that plastic surgeons do? How many people have heard of skin graft? What's a skin graft? Exactly. Basically, they take skin from somewhere on the body to actually to replace another like burn, for example, or a gone patch of the body. Obviously, do they just choose skin from absolutely any part? No, they try to match the what? The stiffness constant of that patch of skin as much as they can with the one that where they're actually transporting that skin. Okay, so basically, newtons per meter. K tells you how many newtons of force you need to extend it by 1 meter. Remember, because it's 1 to 1. This is 1 right here. Oh, this is 1. So it tells you how many newtons of force do you need to stretch or compress a spring by 1 meter of distance. By the way, you almost never stretch it by what? 1 meter. You never do. You usually stretch it by a few centimeters or a few inches. But in general, think of it this way. By the way, okay, sometimes if you try to stretch a spring beyond a certain length, what happens to it? Actually, it might not very, but at least it definitely what? Think of a rubber band that stretch way too much. What happens to it in the middle? Do you notice some color change? Have you ever tried to stretch a rubber band and then you see kind of like a pale white in the middle? What happened there? Or how many people know about stretch marks? I've got some stretch marks. Right here. Right here.
Yeah, I don't have.
You know why?
Why?
Because every guy, when they go to the gym, what's the exercise they do 24/7? Biceps curls. Everyone is biceps curl, right? But the problem is you do it what? You do it 6 days a week. What's so stupid about that? Are you ever supposed to do the same exercise 6 days a week? What do you need to get the muscle? Time to what? Time to what? Because when you actually work out, what do you always do? What do you do to the microfibers in your muscles? You literally rupture them, you break them, which means what? They need time to what? Exact same thing with a spring. Because when you stretch it, and if you stretch and then you don't give it time or chance to go back, and you stretch it once more, what's going to happen to the bonds within the body of the spring? They're going to what? They're going to deform, and once a bond breaks in an elastic manner, what happens? Can it ever go back? Absolutely not. You see what I mean? By the way, the opposite of elastic is plastic. So when a material stops being elastic, it becomes a what? A plastic material. That's why you always hear elasticity versus plasticity. Elasticity is being what? Flexible. Plasticity is being what? Rigid. Okay, so always remember that. So basically, if you could stretch a spring to 1 meter of distance, and it could take that, if you let go, what happens to it? It's going to go back to what? It's going to go back to its natural length. The amount of force you need to stretch it by what? 1 meter of distance is called the what? It's called the what? The stiffness constant, okay? How many newtons did you need to do that? Okay? All right. Now on to the energy. Ladies and gentlemen, here is the equation of the energy stored. Remember, stored. Because again, everyone, all energies are what? Except for kinetic energy, what one word can you pin next to all the other energies again? Potential. All energies are potential, which means all energies are stored until released in a kinetic energy manner. The energy stored in any spring compressed or stretched is always equal to that. Is this equation similar to another equation mathematically that we did before? Yes, which one? Exactly, EK. EK was the same mathematical structure. EK was half as well, but instead of K, we used to have what? M, the mass, and instead of the stretch, we had the what? The V, exactly, the speed, okay? What do physicists and engineers and scientists in general always do whenever they invent a new equation? What do they always check? The units. They always check the units just to make sure that the unit checks out. So we are hoping that if we plug in the units here, we get what for E? What's the unit for energy all the time? Joules. Okay, well let's see what happens when you actually do that. All right, let's check the units. What was the unit again for K? We just did it on the previous slide. Newtons per meter. How many newtons per 1 meter of extension or compression? And what's the unit for delta X? But it needs to be squared. All right. There we go. Half obviously is what we call a dimensionless or a unitless number. K is this guy. M is this guy with a square. Okay, what happens to these two? One of them cancels, so this power cancels with this power, which means we get what? Newtons times meter. And no surprise, again, the equation is built to always basically identify with a single joule at the end. Okay, so this unit, as far as we're concerned, this unit gives us a joule. All right. So I'm gonna give you a few simulation websites. Yes. So here, what do we have here? We have a spring and we have what basically what we call a force meter or a force application device. Okay. So what we need to do here is basically what all I'm doing here is I'm trying to show you that the equation Hooke's law, which is what remembers Hooke's law? Force spring equals what times what? Come on, Hooke's law. We just did 3 slides ago.
Equals K delta
Okay.
X.
Times delta x. Okay, so here, let me see if I can zoom in. Can't much. Okay, no problem. So everyone, let's say that, okay, let's say that you spring constant, by the way, the spring constant here goes from 100 to what? Yeah, obviously it could go lower, it could go higher, and any positive number is accepted, as long as it's not 0. Okay? Applied force. So let's say, for example, everyone, that you have a 600 Newton per meter spring, and you apply a force, let's say, of 50 newtons. Can we actually calculate right now by how much from the equilibrium position the spring was stretched?
Yeah.
Yes, using what law? Hooke's law. All right, so let's actually do it. Here we go. What's Hooke's law? F equals, or F spring equals K delta X. All right, which one am I trying to solve for here right now? We're trying to see how longer it got, so yes, the change in length from the original positioning. So delta X equals what? Fs over what? K equals, all right, how much force did we apply? How much? 50. And the stiffness of the spring was what? 600. All right, so 50 divided by 600. How much is that? Well, I know that a 0 cancels with the 0, and it's 5 over 60, which actually simplifies to 1 over what? 1 over 12. How much is 1 over 12 as a decimal? Comes for physics people. How much is that? This is 0.08, I believe, 3. In what unit? In meters. Okay, let's actually see. So I'm going to show the applied force. All right, so first problem. 0.065, sorry, 0.65 kilogram mass hangs at rest from a spring. The spring is seen to be stretched by 0.44 meters from the equilibrium position. What's the equilibrium position? It's the position when there was no what? No stretch or no mass attached to it. Question is, what's the spring constant? How stiff is the spring? If it takes that much mass to stretch it by almost half a meter, how stiff is the spring? By the way, just for a look at the numbers. Do you think this is a stiff or a loose spring? Why? First of all, how much mass do we have?
Very little.
650 grams, like maybe not even this much. How much did you stretch it by?
Almost half a meter.
Almost half a meter, like half a meter thick, this much. Now that's not a stiff spring. Okay, so what's the equation? We are doing, okay. So obviously we don't have force, but we have mass. So if you sketch the spring, everyone, by the way, get used to this way of sketching spring. Either I'm gonna stretch it like this. Seriously, many people sketch a spring like that because usually that's how springs look like, looped coils. Or, you remember that symbol back from 3U physics? I'll give you a hint, it was in the electricity unit, in a circuit. Resistors or resistance, exactly, yes. Either way you sketch it, I will accept it, okay? So, everyone, here's the what? Here's the mass connected. So my question to you is this mass moving or not? What does the question say? Come on. At rest, which means, as far as I'm concerned, what Newton's law applies to this mass? First, second, or third always. First or second? First. So that means how many forces are acting on this mass? 2. Its own Fg, but what's holding it up? See, we can call it anything, right? We can call it force applied. We can call it force what? Force spring. Let's call it force spring. Fs. Okay. Nora, are those two equal for now? Yes, they are, because the spring, sorry, not the spring. The mass is neither what? Moving down, nor what? Moving up. So that means Fs must equal Fg. Do we have an equation for Fs? Yeah, only so far, only one equation we have for Fs. What is it? Hooke's law. K times delta x. K times delta x equals, what's the famous equation, never changing for Fg? Mg. Now do I have all the numbers I need? What do you think?
Yes.
I sure do. I know the extension, I know the mass, I know the g. Great, let's solve for k. So now k is k equals mg over delta x. Okay, how much is m? Point what?
65.
Which is always good because it's already in kilograms, times 9.8 divided by, good, also 0.44 in meters. Done. That's it. Let's calculate this number. 0.65 times 9.8 divided by 0.44. Ready? 14 point, what's the secret situation? Is it 2?
Yeah.
It is 2, yes. So, to 2, that would be where's what? Just 14, because it did not cross the half. So 14. Everyone, 14 what? What is the unit for K? For the stiffness of the spring? No, there is. Remember, okay, Josh, so far the only things that have no units that we studied are what? The mu's, right? And the cosines and sines and so on. So this one has a unit because it relates a force to a distance. So what is it? Newtons per meter. Right? Because remember, this is how stiff it is. Apparently, not so stiff. How many newtons do you need to stretch it by how many meters? Wow, it only takes 14 newtons, which is almost nothing, to stretch it by this much. Yeah, that's a very loose spring. That's a very loose spring. Okay, let's look at part B. You remove the mass from the spring and you attach a what? Another mass. Now you see that the new, by the way, is it still the same spring? Also, is it still with the same stiffness constant? Yeah, by the way, how can you change the stiffness constant of the spring? You need to screw up the spring, right? Like you literally need to what? You need to stretch it way too much, so it becomes what? Looser. Now you have a what? A lower K. But we're saying, you know what? The K is still within the, sorry, the spring is still within this what? Tolerance range. Okay, now you need to know the what? The new mass. Are we still gonna apply the exact same equation? Yes, it is, because everyone, look, everyone, you hang it, and you let it stretch until it just what? Stops. When it stops, we're back again to this FBV. Okay, which means we're back again to that FS. Sorry, I mean to that equation. So for part B, what is it? It's going to be, I mean, you can definitely jump to this equation, but tell me, everyone, which one are we solving for now here? The mass. So I need to rearrange in a mass way, which means I need to divide the K delta X by G. So M equals K delta X by G, which is equal to, again, we already calculated the K, right? It's the same K. However, I'm going to go back and take one more digit from the original value, which would be what? 14.5. So 14.5 times, how much did we stretch it by now? 0.74. So what do we expect? Lesser mass or more mass? More. It's stretched by more, which means there's more gravity on it, which means it has a bigger weight. All divided by 9.8 equals, and we just do the math, 14.5 times 0.74 divided by 9.8. 1.1. 1.1 what? What's the unit? I'm sorry. Mass, so it has to be kilograms. Okay, a spring-loaded toy uses a compressed spring to fire a marble out of a tube in any way, this way, whatever. So you compress and then you let go. So the energy stored in the spring fires it opposite. A force of 220 newtons apparently compresses the spring by 0.14 meters. The question is, how much energy is stored in the toy spring? Okay. Are they asking for force or energy there? Energy. What's the equation for energy? It was E half K delta X squared. Problem is, I only have the delta X. I don't have the K. Well, not right now. Do we have enough information to calculate the K? Do we have information to calculate the K?
We have the force.
We have the force and the extension. Perfect, everyone. The K is there. You just have to calculate it on the side. So, on the side, I'm just going to move this here. All right, so K is equal to what? 220. That's how much force it took, divided by 0.14. By the way, do you think that's a stiff spring? I think so. 220 newtons to only stretch it by 14, which is about this much. Yeah, that's somewhat stiff. 220 divided by 0.14. Wow, you need 1,571 newtons to stretch it by 1 meter. So 1571. I'm just gonna stop there. 1571 newtons per meter. Great. Now I'm ready to what? Take this number and put it right here. So half 1571 times 0.14. Boom. All right, let's do this math here. By the way, everything is gonna be in joules at the end. So 0.14 first times 1571 times half. It's only storing about 16 joules. That's it. Sig figs is 2, so 15. Okay. And that's all we need to know about the basics of what Hooke's law and elastic energy equation. Okay. Now let's go to the bigger picture. Whenever you combine a bunch of energies, what law of the universe do you always have to contend with? Whenever you have a bunch of energies in the system, what law or principle do you have to apply?
They must all add up to.
So what's the official name of the law? Conservation of energy. Now we just have to what? Add another player to the mix. Now we don't just have EK and EG, we also have what? EE, yes. So things are going to get more complicated, but definitely more interesting for sure. Okay, so conservation of energy with springs. So just like a simple system can have only kinetic and gravitational, when you deal like throw a ball and goes up and down according to under the influence of just gravity. You add a spring to the mix, guess what? Oh, you add a spring to the mix and the spring is being what? Compressed or stretched. Then that means what? There's some energy of the system that's being what? Stored in the spring, which means the spring now has a say in the equation. So the only difference now, instead of 2 bars adding to the. By the way, what does T mean now? So I can't call it what? Come on, I can't call it mechanical. Mechanical only applies if you only have what? K and G. So here you can call it M. But when you add absolutely any other energy storage, you have to call it what? Total. By the way, could you have called it total in the beginning, like with K and G? Yeah, it's the same principle, but it just has a special name when you only have 2 players, K and G. Okay, so now, by the way, question for you. Someone says, if this bar goes down, sorry, my bad. If this bar goes down, those 2 have to go up. Does that always have to be now? No? Could it be?
Yeah.
It could, but you know for sure that if one bar goes down now, at least what? One of the other 2 must what? Must go up. And the other could what? Could stay the what? Exact. So now we have more possibilities and situations. Okay? Alright. So Okay, I'll show you this after we do the problem. Okay, so everyone, let's look at this problem. Okay, here's the question. A 3.5 kilogram mass, by the way, get used to these problems. When we do the university problems, I'm going to show you some pages from the university textbook. They love questions where blocks are placed on ramps and at some point they're hitting a spring. It's always happening. 3.5 kilogram mass slides. Okay? Does that mean anyone have to push it? Nope. A tilt with the gravity is all that's needed. Slides from a height of what? 2.7 meters above the ground. By the way, could I have given you the length of the ramp instead of the height above the ground? I could, but then I would need to give you the what? I would need to give you the what? The angle to apply some quick SOHCAHTOA to find the what? To find the height above the ground. Okay? But for this one, they already given you the height of the ground. Okay. The spring compresses once it's being touched by the moving block by 26 meters before it comes to a what? A stop. The question is, how stiff is the spring? Okay. Remember, the best way to do any energy conservation problem is to look at what each instance of the what of the problem. First, where was the block? On top. Okay. Was it moving? Yes or no? No. No. At the beginning. No. So what energy was definitely zero? Good. Was it elevated? So what energy is not zero? Okay. Was it touching the spring yet? So the spring was neither compressed nor. So did it have any energy stored in it? So that means what? Right there, right here, what's the only energy that's non-zero? Gravity. No, not zero.
Oh,
Not zero. Which means the entire energy of the system was purely of what kind? Perfect. So I want you to do this now. Here, I want you to write EK equals 0, EG equals question mark, and EE equals also what? Okay, 0. Now, I want you to imagine the block is sliding down. As it slides down, what energies change? Kinetic. What happens to it? It increases, of course, because it's speeding up. Okay, so the EK bar goes up. How about the EG bar? What's happening to the height or the elevation? Goes down. How about the EE bar? Still what? Still untouched. Good. Hits the ground. What bar goes down completely to 0? EK or EG? EG, because now the elevation is 0. What bar goes all the way up? EK, because now it hits maximum speed. What stays the same from here to here? Speed, because there's no what? There's no friction. Nothing is stealing energy from the EK. Okay. Hits. Starts to what? Starts to push. If it pushes on the spring also what? Pushes back. When something pushes you back, are you speeding up or slowing down? You're slowing down. So, as it compresses, what happens to the EK bar? What happens to the EE bar? At the moment it comes to a stop, what bar is maximum? EE. What two bars are completely zero? Do you see how I always think of energies? I always trace the story from the beginning to the end. Okay, so here, everyone here, although technically this is not that important to us, I want you to write EK is a number, EG equals EE, both what? Both 0. Finally here, EK is 0. Again, I'm talking about when it what? When it comes to what? When it comes to us, not as it's compressing, or not when it touches the little platform of the spring. When it completely compresses as much as it can. EG is 0, and EE is a number. But what's the quantity that's always conserved? Always. Say again? Which quantity is always conserved? Those are not conserved, obviously, because they're changing all the time. What is always conserved in the system the whole time, from beginning to end? the mechanical, or in this case, we call the what? The total energy. Perfect. So now we go to what? We actually, by the way, the easiest way to do this is just to say what? E total initial is equal to what? E total final. So you can just say this, E T initial must equal E T final. Well, apparently, ET initial was what? EG was, actually, I want you to write all three. Let's write EK plus EG plus EE. Also here must equal EK plus EG plus EE. And some other teachers might say, well, you still technically have to say KI, JI, EI, KF, GF, EF. That's fine. As long as you have at least each one belonging to either the instant, initial, or final, I'm fine. Can you tell me which ones are zero on the left side? Which ones are zero on the left side? Which one were zeros when it began to move? Exactly. Initially, this was zero, and this was zero. Finally, what was zero? Finally. Yeah, when it came to a stop. Amar?
Gravity.
Gravity, because it reached ground level, and perfect. Done. So we are saying about this system that all of the energy gravitational at the top converted to elastic compression energy at the end. Done. Just plug in the numbers. So mgh, mg, well technically h initial, equals half k delta x. You might want to say, oh, it's the delta x what? Sorry. Delta x what? Squared. Technically, you might want to say, should I have to say delta x final? Well, I mean, we only say delta x when it stops moving. So it's completely up to you. All right, which one of those variables am I solving for? The stiffness constant. Which one is that? The K. So how would you play with this? Well, honestly, the easiest way you can do this, K equals, just divide all of this by half delta x squared. Sure, that could work. Unless you want to do it, for example, Ahmed's way sometimes, multiply everything by 2. Yeah, that's if you want to do it in steps. But nothing says that what I'm going to do that right now is wrong. NGHI, all divided by half delta x squared. Okay, plug in numbers. What's the mass of the block? 3.5 kilos. Gravity is 9.8. Initial height was 2.7. Half. How much was it compressed by? 26 centimeters, so 0.26, and don't forget the square. Done. So 3.5 times 9.8 times 2.7. Divided by, open a bracket, instead of half as a fraction, just put 0.5 times 0.26 squared. Bracket. Wow, quite a stiff spring. 2,700 and almost 40 newtons for a single meter of extension. All right. By the way, just to tell you how big 2,740 newtons are, I'm going to compare it to my own weight, not mass, weight. So let's just write the number first. 2,000. Oh, what's the scientific situation? 2. So that would be 2,700. So 2,700. Oh, 40 would be what? Newton square. Now, how would that compare to my own weight? Well, first of all, I need to compute my own weight. How do you always calculate your weight? You just multiply what by what? It's your FG. So my mass, so for example, 62 times 9.8. My weight about 600 what? My weight is in what? It's a force, it's in newtons. So if you divide 2,700 divided by 610, you need to hang 4.5 people with my mass. You need to clone me 4.5 times. Hang that from the spring, and then you would see it stretch by how much? How much? 1 single meter. That's how stiff that spring is. it's equal to 4.5 physics teachers. Okay? All right. So let's look at the problem here. So what do we have? Yes. Okay. So what do we have here? So we have a 0.35 gram branch, okay, for some reason splits from the tree and what? And what? Falls. So initial velocity is what? If something falls, it basically is dropped. So that means the initial speed is there. So onto a trampoline. Trampolines are made of what? What's the body, the mesh of the trampoline is made of what basically? It's made of basically of something that has spring behavior. So it could be compressed or deformed or stretched. If the branch was initially how far? 2.6 meters above the what? Above the trampoline, not above the what? Not above the ground, okay? In fact, do we even know how high the trampoline mesh is from the ground? We don't know that. Okay, that's fine. And the trampoline compresses or goes down just 0.40 meters by the time the the branch hits it, or sorry, compresses it. Find the spring constant of the trampoline. If this was a legit spring, how much stiffness constant? How much stiffness constant would it be? Would it have? Would it be more of a slinky or more of a what car shock absorber, like the really heavy industrial one? Okay. All right. So basically, an animation would be like this. Okay. Sorry. Oh, the animation is not there. All right. Now, right here. What's the energy? What are the energies involved in all the problem at any instant? What are the energies involved? They are the big three, which are what? EG, EK, and EE. Okay, right here, everyone, right here. As the what? As the branch started to fall, what's the EK? Practically 0, because it just what? It just started what? To move, which means initially the speed was what? 0. Okay, what's the EG? Is there some EG here? Well, of course, it's elevated. Above what? Regardless, it is elevated, which means it's EG. Its EG is not 0. How about the EE at that instant? 0, because the spring is what? Not under any action yet. Okay. Falls down. Falls down. What's happening now to the EK and EG? The EK is what? Getting bigger, and the EG is going lower. How about EE? Still what? Still maintained at 0. Touches. Okay. When it touches the trampoline, does it come to an instantaneous stop? Nothing in the universe stops at once. Everything takes what? Some time and some distance to it to decelerate. Okay, so obviously, why would it decelerate? Because it starts pushing on the trampoline. So the trampoline starts to push what? Back by Newton's third law and by also what? Hooke's law. Okay, so as it now pushes on the trampoline, is it still in motion? It's still in motion, although the motion is what? It's decreasing or slowing down, but there's still motion, which means there's still EK, although the bar is even getting smaller. How about EG? Now, question for you, everyone. At the moment it touches the trampoline, what's the EG? Okay. Technically, could it be positive, 0, or negative? It depends on what? Come on, remember, every problem when you have EG in it, you have to what? We have to agree on a what? Not direction. On a reference height or reference elevation. Now, so let's look at the 3 possible cases. Most commonly, what's the reference elevation? Most commonly, the ground. If you set the ground to be the reference elevation, that means the branch at any moment will always have what kind of EG? Positive, because it's always got to be what? Above. Okay. What if you set the initial height or elevation of the branch to be the reference height? Then that means the what? The branch is always going to have what kind of energy? Negative after it starts falling, because once it starts falling, what's EG? As it starts falling, and then it's going to go below the reference height, which means it's going to develop what kind of EG? Negative. How about if you set the what? The level of the trampoline to be the reference height? Then what's going to happen? Before it touches, the EG of the branch is going to be what? Positive, because it's above. After it touches and starts going down, the EG of the branch is going to be what? Do you see how it makes a huge difference? By the way, are the EE and the EK ever going to be affected? No, because they don't depend on what? On your reference height. They depend on speed and the compression of the spring. Okay, so what are we going to set as the reference height? We're going to set what? The trampoline. What is so bad about setting the ground as the reference height? Josh?
we have no idea how far the what? The trampoline is from the what? Is from the ground. You still can do it. I'm going to show you how, but I would discourage you from doing so. It's just going to introduce what? An extra variable. It's going to mess up the math until it cleans up at the end. But we'll do it the easy way first. So, so everyone, we're going to do, so I want you to do this. Go ahead, put a dashed or a solid line, whatever, exactly at the level of the trampoline. And what should we write on this? So we can call it reference what? Reference height or reference elevation. Or if you remember yesterday from the animation I showed you, they just call what? H equals what? H equals 0. Once you say H equals 0 on the diagram, that becomes your way of telling me this is my reference height. Okay? So right there, what's the EK right here? What's the EK here? 0. What's the EE? 0. What's the EG? Something. So you can just say what? Just say question mark. Okay. Right as it touches, what's the EK? Is it still in motion? Everyone, the moment it touches the trampoline, it is still moving. Of course, it did not come to a stop yet. It's going to take some time. At the moment it just touches, it's still in motion. So everyone, I want you here above the trampoline to write EK equals number. How about EG? How about EG at the moment it touches the trampoline? We said it will be 0 because it's at reference height. So EG equals 0. How about EE at the moment it touches the trampoline? Has it compressed it yet? No, it just reached its own level, which means technically, what's the EE at the moment it touches? Also 0. It has not pushed force into it yet. So EE. Bless you. All right. By the moment, I don't know if you can do this on your diagram if it's big enough, but I can do this. Look, everyone, eyes on the screen. Oh, my bad. Sorry. I want to do this. What does that represent? The trampoline sideways as it fully gets compressed and stops. So right here, everyone, right here, when it comes to a stop, what's the EK? So it compressed, but then the spring was like, that's it. You can't go any lower. So what's the EK? 0. So everyone down here, EK equals 0. How about EE? How about EE? Is it 0 or some number? Yeah, it's a spring that's been fully stretched. EE is some number. EE is some number. How about EG? It's some number, but it's what? So let's just call it also question mark. There's no need to put negative question mark. Just call it question mark. So EG equals also question mark. So far, so good? The tracing method will never fail. And it will always organize your thoughts into the solution. My question is, what type of energy is always conserved? Never above or below 100%. Say again? Total. So that means I can add the 3 at any instant and make them equal to the what? To the 3 added in any other instant. Which 2 instances do you think we should relate? I mean, you could relate always any 2 instances as long as you impose E total is 0. Sorry, E total is conserved. My bad. Which 2 instances do you really think we should relate? Or which instance here is not relevant? Ahmed? So like top, middle, or bottom? Which 2 should we relate? Top and, yeah, because I know what happened here. I'm given information about the compression. Really don't care. Okay, what information could you ask me that would require me to what? To consider the middle case? What could you be interested in the question to ask for me to actually have to look at the middle case? I'll give you a hint. Both EE and EG are 0. So really, I can't know much about anything that goes into them. So what's the only thing I could be asking about? This speed, yes, I could ask you at what speed does it hit the what? Does it hit the trampoline? All right, okay. So now let's what? Let's go to the solution page. All right. Okay, so how do we start these kinds of problems, especially the way we did it yesterday? What's the first statement you write? There's a more important statement we say first, which that what energy is always conserved? Total. So everyone, top here, we're gonna say ET initial equals what? ET final. Okay. ET comma initial equals what? ET final. And now what am I gonna do? I'm gonna start expanding things. Okay. I have 3 values, so I'm just gonna put the three players. So E K initial plus E G initial plus E initial must equal E K final plus E G final plus E final. Okay, I can cross some of those out. Basically, I can cross some of them as zeros. Which one? In the initial step, which one or which ones were zeros in the initial instant? EK, good. So everyone go ahead, cross this out and just put 0. Also what? EEI, yep, boom. How about the final compression step? EK, because it came to a stop. How about the other two? We don't know. They're non-zero, so we have to find them, or we have to basically incorporate them. Okay, now what can I do? I have to start doing the what? The equation. All right, what's the equation for EGI? MGHI equals EGF MGHF plus half K delta X. Okay? So far, so good? No, it's not. I, on purpose, made a very huge mistake here, which, by the way, could actually completely destroy the answer. X squared, your displacement in the energy equation is what? Is what? Is squared. But your displacement in the Hooke's law is what? Not squared. Remember, Hooke's law is the force one. F spring equals what? Just K delta X. But in the energy one, it's what? It's squared, okay? By the way, listen up. There's a reason it's squared. Listen up. The reason is, in university, they will teach you. Listen up. In university, they will teach you. You have to choose a positive direction, right? So if you compress a spring, it's opposite than what? What's the opposite of compressing? Stretching it. They will tell you, you have to decide which direction is what and which direction is negative, which means you have to decide, is my stretching direction positive or is my what? Compression direction positive? Which means this could be what technically? Positive, or if you put it negative and you forgot to square, can that actually really destroy the problem? Of course it does. But when you make it a square, what happens? It always comes out to be, which is the proof that the energy stored in the spring, whether you compress it or stretch it, is always the what? The same amount. That's the key. So go ahead and, oh, my bad, squared. Do we have enough numbers to plug in? Pretty much. Can you still do this as a symbolic manipulation? Of course you do. By the way, what of these are we trying to solve for? K. So you know what? But let's plug in the numbers. Okay, what's the mass of the branch? Come on. 0.35. So I'm going to start here. 0.35 times 9.8 times, what's the initial height, elevation of the branch? 2.6. Positive or negative? Positive, because it's above the reference height. Equals, same thing, almost. 0.35. 9.8. I don't know. You tell me. The distance is from the reference height. Amar. Should be what? Negative. Where did it stop? At what distance? 0.14. Where? Above or below? That's it. Negative 0.14. Done. Awesome. Plus, we have Yes. Hold on. Uh, I do not know how high the trampoline is. So that's why I chose its own height as the what? As the 0. Oh. Oh, yes, everyone. If you know the height, 100%. But everyone, listen up. If you know the height of the trampoline, come on, everyone, focus. If you know the height of the trampoline, and you chose the what? You chose the ground to be your reference. How would you calculate how high did it stop above the ground? You have to subtract the what? The elevation of the trampoline minus the what? The 0.14. Yes, if that's the case, and that's technically what I'm going to do for the next kind of the solution method. Okay, plus what? Half. Okay. Okay. Does it matter if I put this one as positive or negative 0.14? Not really, because it's going to be squared. It does matter sometimes with the force, but not with the energy because it's got to be squared. Although, by the way, any university, they will be very adamant about you still deciding which direction is negative or positive. And if you decide to be negative, you have to plug it here as negative. But since we are squaring, I'm not going to care because it's a magnitude thing. All right, let's plug in the numbers. Who can tell me what this whole thing is? The triple product on the left side. Come on. 0.35, 9.8, 2.6. I know this one's got to be negative by default because negative will win. And this will be, sorry, 8.9, sorry, 18. And this one is negative, something much smaller, obviously, because 2.6 much bigger than 0.14. This is, what type of 190? Sorry, 0. Oh, 4802. Wow, very small. This is point 0.098. Oh, well, so square this. Sorry, how much? Yeah, but then we multiply by half. How much? Point 0.0098. All right. Are we good for that last number? Okay. It's 0.14 is 0.14 is 0. Yeah, you're right. Okay, what do I do now? Oh, what am I missing? In the very, very last term. Okay, yes. Obviously, you don't have anything to solve for. All right. What do I do? Easy. I'm going to move this one here and divide. Well, after adding. So K is going to be 8.918 plus 0.4802 0.0098. How much? By the way, right before we solve, what's the unit always for K? Always. Newtons per 1 meter of extension. Very good. Okay, let's see how stiff this spring is, or this mesh of the trampoline is. Who's got this? I think the answer from last year was like 900. 959 newtons per meter. What's the specific situation for the whole problem? 2. So this would be definitely much closer to what? 960. Take the ground now as the what? As the, what do you call it? Come on. Duplicate slide. There we go. As the reference height. Yes. Okay. So what I'm going to do is zoom in and start deleting things. Okay. Obviously, what the first statement changed or stayed the same? First statement. First statement stays the same no matter what physics problem you ever do. Okay. Now, we're going to take, by the way, don't copy this. I just want to show you how difficult it's going to, not difficult, more elaborate it's going to be. Okay, everyone. If you set the ground to be 0, does it change the fact that the initial kinetic energy and the initial energy of the elastic of the mesh is going to be 0, or would it stay? If you so would those change? Never. The branch, regardless of your reference height, the branch started from no motion and the spring was not touched. However, if you put the ground as what? As the 0 level, Does this one stay at 0 still? Yeah, because it still came to a stop. But what does this one become now? No. It's what? It's still what? It's still positive because it's still what? Above the ground. Above the ground. Okay. So now let's what? I have to change all of these now. Look, everyone, I have to change all of these. Okay. All right. Listen up. Do I know how high the trampoline is from the ground? No. So I have to call it a variable or a parameter or a symbol. What do you call it? Anything you want, as long as it's not one that we use. N? I would call it lowercase d. Okay? All right. So what was the initial height of the branch? It was 2.6 meters above the trampoline. And the trampoline itself is d above the ground. So how much is the branch above the earth or above the ground? D plus 2.6. Perfect. So mg, mg, and this would be d plus 2.6. Keep going. mg. Okay. What is the final height or the final elevation of the branch? Now we know the 2.6 have been completely cleared. Also, how much did it dig into the mesh? 0.14. But it's what? It's above the ground. So it's D minus, you got it, plus 1/2 K. Okay. What about the delta X? Yes. My bad. Thank you. Force of habit. Thank you. So everyone look. 2.6 mg, 2.6 mgd, mgd. What happens to these two? Yeah, because you can just say if I have the same amount added to both sides of the equation, I could take it out, or you can move this one here and it cancels. Okay, so I was good. Sorry, I didn't see it. And then that got the same exact answer. But what did I have to introduce? What did I have to introduce into the system? I had introduced a new variable, which is what? Which is the height of the what? Of the trampoline.